So what we have here is a wavefront sensor. It's used to measure the wavefronts, optical wavefronts. It can be used for optical shock testing, or we use it also to drive deformable mirrors. And here I have a very simple demonstration setup. It's not a real thing, it's just a demonstration setup. So we have a micro lens raster in front of a camera, and when we get an image, then basically in a computer we just acquire a pattern of spots like here. Now if I, for instance, if I introduce aberration, which is in my case would be just spectacles, I just put it here in front of sensor and I acquire the second image. Now I can process these two images and see what happens. So you see that we have very, very little astigmatism here, and this is because we remove all the spherical part. And because, well, it's ignore defocus, it says ignore defocus. Now it will not ignore the defocus, and it will tell us how many diopters. Yeah, you see. Well, now it tells us that I have 2.6 diopters in my spectacles, and very little astigmatism, probably just due to the tilt. When I put it in the setup, I cannot keep it under the right angle. This setup can also work in like in real-time alignment mode. So if I go to here to processing and say loop is then it shows in real time. It shows how much tip tilt, defocus, astigmatism, coma, and everything, and also in polar coordinates. So I can, for instance, just to show, I can misalign the system right now. So I just move one lens, and when I move this lens, I just turn this screw, look, and you see that this spot goes down because, well, we have introduced misalignment of the system, and this bar also goes down because, well, we introduced defocus, and this bar goes down because it's astigmatism. So basically, using this, you can very precisely align optical systems. And it can be also automated, like not with hands, because you have too many parameters, but it can be done just with stepper motors or something like that.